On May 26, 2025, Suzuki temporarily halted production of the Swift at one of its plants in Japan. The problem was not steel, not batteries, not computer chips. It was a shortage of components linked to rare earth magnets after China introduced new export controls on several medium and heavy rare earth materials. A modern car contains thousands of parts. Yet a permanent magnet, small enough to hold in your hand, can become the part that stops the line. That sounds like a story about scarce minerals, but it is not. Rare earths are mined in several countries. Large deposits exist far beyond China. The strange part is what happens after the rock leaves the ground. Japan had already confronted this problem 15 years earlier. In late September 2010, rare earth exports from China to Japan slowed sharply. Japan's Ministry of Economy, Trade, and Industry later described shipments as stagnating for about 2 months. Tighter customs procedures were cited at the time. The episode is often described as a Chinese embargo, but China never publicly announced a Japan-specific ban, so the exact formal mechanism remains disputed. For Japanese industry, the practical lesson was much clearer. A critical supply chain could suddenly become unreliable. Japan responded with a broad diversification strategy. Government-backed institutions invested in alternative suppliers, most notably Lynas in Australia. Companies worked to reduce rare earth use where they could. Japan supported recycling. It expanded stockpiles. And it looked for supply outside China. Those efforts produced measurable results. According to Japan's Trade Ministry, China's share of Japanese rare earth imports fell from about 85% in 2009 to 58% in 2020. That is a real success. But it did not recreate every stage of the supply chain. Japan could buy more material from somewhere else. It could hold more inventory. It could redesign some products to use less. Those steps mattered, but they did not automatically reproduce the industrial system that sits between raw material and a finished magnet. Reducing dependence is possible. Recreating the entire chain is much harder. Look only at a map of rare earth deposits, and China's position can seem confusing. China has enormous resources. It is also the world's largest miner, but it does not own all the rare earths underground. The United States Geological Survey estimated that China produced about 270,000 tons of rare earths in 2025, out of roughly 390,000 tons worldwide. That is close to 69%. Dominant, yes. A geological monopoly? No. The United States mines rare earths at Mountain Pass in California. Australia mines them at Mount Weld. Other production comes from countries including Myanmar and Thailand. So if the material exists elsewhere, why is the system still so concentrated? Because a mine is not a supply chain. For the rare earths used in high-performance magnets, the International Energy Agency estimates that China accounted for about 60% of global mining in 2024. Then the material moves downstream. At refining, China's share rises to 91%. At sintered permanent magnets, it reaches 94%. Those are different stages of the same chain, and the deeper you go, the more concentrated the system becomes. Ore first has to be mined and concentrated. Then the mixed rare earth material has to be chemically separated into individual oxides. Those oxides are turned into metals. The metals are blended into precise alloys. The alloys are milled into fine powder, pressed into shape, aligned in a magnetic field, sintered, heat-treated, machined, and coated. Only then does the material become the compact, powerful magnet that goes into motors, generators, electronics, and industrial equipment. The critical map is not the map of where the rocks are. It is the map of who can transform them. Rare earth separation is difficult for an awkward reason. The elements are chemically very similar. A mixed concentrate does not arrive as neat containers of neodymium, praseodymium, dysprosium, and terbium. They have to be pulled apart from one another repeatedly until each stream reaches the purity required by industry. At scale, that means long chemical separation circuits, careful process control, large volumes of reagents, and waste streams that have to be managed safely. This is the technical core of rare earth processing. And it is not a generic refinery that can simply switch from one mineral to another. Different ores bring different impurities. Different product mixes require different separation sequences. The plant has to achieve purity, recovery, and consistency at the same time. A country can discover a deposit. It can permit a mine. It can even produce concentrate, and still be missing the stage that turns that concentrate into useful industrial material. But the chemistry is only part of the moat, because even a separated oxide is not yet a magnet. After separation comes another sequence of specialized industries: metal refining, alloy production, powder processing, sintering, coatings, precision manufacturing. For the highest performance magnets, the challenge also includes intellectual property, specialized machinery, accumulated process knowledge, and customer qualification. The International Energy Agency has highlighted one advanced magnet process called grain boundary diffusion. It is heavily patented. And the agency reports that specialized equipment for the process outside China is unusually scarce and expensive. Then there is qualification. A magnet factory can exist on paper before an automaker or aerospace customer is ready to trust its output inside a product expected to operate reliably for years. Purity has to be consistent. Magnetic performance has to be consistent. Coatings, dimensions, and thermal behavior have to meet specification, batch after batch. So building a non-Chinese supply chain is not one construction project. It is a sequence of industries that all have to work at the same time. That creates a second problem. Even when a country decides this supply chain is strategically important, the market can make it difficult to sustain. Mountain Pass is the clearest example. The California mine once helped make the United States a major rare earth producer. Years later, Molycorp tried to rebuild Mountain Pass as an integrated American rare earth business. The timing seemed favorable. Rare earth prices had surged after 2010. Capital poured into new projects. But building the plant and making it work consistently were different things. By late 2014, Molycorp was reporting Mountain Pass production below expectations, operational interruptions, and large losses. At the same time, rare earth prices had fallen sharply from their earlier peaks. In June 2015, the company filed for Chapter 11 bankruptcy protection. The lesson is not that China deliberately bankrupted an American company. The public evidence does not establish that. The more important lesson is structural. A country may want a second supply chain for security reasons, but the company building it still has to survive commodity prices, operational setbacks, debt, and years of expensive learning. Strategic value and market value are not always the same thing. That mismatch helps explain why diversification can look essential during a crisis, then become much harder to finance after prices fall and urgency fades. The security benefit belongs to an entire economy. The commercial risk sits on one company's balance sheet. The latest American attempt at Mountain Pass is being built around that problem. MP Materials now operates the mine. In December 2025, it began manufacturing neodymium iron-boron permanent magnets at its Independence facility in Fort Worth, Texas. But the chain is still being filled in. In its filing for the second quarter of 2026, MP Materials said it expected to begin refining heavy rare earths in the second half of the year, with initial production of terbium and dysprosium. This time, government policy is not sitting on the sidelines. The company's agreements with the United States government include long-term magnet purchasing commitments and a price protection mechanism for neodymium-praseodymium products. Under that agreement, the benchmark floor is $110 per kilogram of neodymium-praseodymium equivalent. In effect, the policy is paying for something normal commodity markets can undervalue: redundancy. That is a major shift. The goal is no longer simply to build a mine that can compete at today's price. It is to keep an alternative chain alive through the price cycle long enough for it to become reliable. And then there is a detail that complicates the image of a perfectly self-contained Chinese monopoly. China imports important rare earth feedstock, too. Myanmar has become a major source of heavy rare earth material that ultimately feeds Chinese processing, including material associated with elements such as dysprosium and terbium. The exact share changes depending on the year and on how the trade is measured. So it is better not to pretend there is one permanent percentage. But the dependency itself matters. It reveals what China actually controls. Its power does not require every ton of ore to come from Chinese soil. Material can be mined across a border, enter the Chinese industrial system, and emerge from the stages where global capacity is most concentrated. The leverage sits in transformation, not simply possession. That transformation system is no longer completely uncontested. Lynas now produces separated dysprosium and terbium in Malaysia. In the June quarter of 2026, the company reported 19 tons of combined dysprosium and terbium production. Earlier that year, it produced its first samarium oxide. MP Materials is making magnets in Texas and expanding its downstream capabilities in California. Japan has spent years building alternative supply relationships. Europe is trying to expand domestic extraction, processing, and recycling. Substitution can reduce rare earth demand in some applications. Recycling can eventually return more material from old products into the supply chain. These are real changes, and the International Energy Agency says concentration in rare earth refining declined modestly in 2025 as new capacity advanced outside China. But progress is uneven. Mining projects are easier to find in the pipeline than fully integrated downstream projects. And announced capacity is not the same as qualified production. New plants still have to commission equipment, stabilize yields, secure feedstock, and convince customers that their material will perform exactly as promised. So the story is not that the world is physically incapable of diversifying. The stronger argument is that downstream diversification has been slower, more expensive, and more difficult than simply opening new mines. And much of the newest capacity is being built with government support precisely because ordinary market incentives were not enough. China's recent export controls made that dependency visible. On April 4, 2025, China introduced export controls requiring licenses for specified items involving 7 medium and heavy rare earth elements. The list included dysprosium and terbium. This was not a blanket ban on rare earth exports. Licenses could still be issued. But the new process created friction in a supply chain built around tight inventories and predictable flows. Some automakers temporarily reduced or halted production as supplies tightened. China announced a broader set of controls in October 2025. One measure would have required licenses for certain foreign-made products when specified Chinese origin-controlled inputs reached at least 0.1% of the product's value. Those October measures were later suspended through November 10, 2026. The April licensing regime remained in force. The legal details changed. The industrial lesson did not. When so much conversion capacity sits in one country, an administrative delay can travel a very long way downstream. We turn to the magnet that stopped the production line. By itself, it is not especially dramatic. Behind it is a mine, then a concentrator, a chemical separation circuit, a refinery, a metal producer, an alloy maker, specialized equipment, skilled workers, qualification tests, and a factory capable of repeating the same result millions of times. That is the hidden system. For decades, China built more of that system at greater scale than anyone else. The rest of the world often focused on the beginning of the chain. Who had the deposit? Who could open the next mine? But industrial power accumulated further downstream. Now the United States, Japan, Australia, Malaysia, and Europe are building alternatives. They are making measurable progress. The question is no longer whether another supply chain is technically possible. It is whether countries are willing to pay to keep it alive when redundancy costs more than dependence. Because the strategic asset was never just the mineral in the ground. It was the ability to transform it, reliably, at scale, into something the modern world cannot easily do without.